Actually, I'm lost. Third talk by Matheus, third and last talk by Matheus. All right, Matheus, the floor is yours.
All right, thank you very much. Well, this is the last hour you get to put up with me. So also, please do interrupt me again at any moment. Um, Martin, just let me know and I'll wait for the person to ask the question. Uh, so I should say the pace was a little bit slower than expected in the previous lecture. So that means we'll cover a little bit less of neutrinos as tools for BSM. So we're talking mostly about this, what I mentioned was a foundational issue of neutrinos as an indication of BSM, which is the neutrino mass problem. And you saw in the exercises, the first kind of one of the more famous applications of introducing a right-handed neutrino or a left-handed anti-neutrino into the theory. And that's the seesaw mechanism. We saw in the previous lecture what the same model with a very small Majorana mass does for you, which is create quasi-Dirac neutrinos. The other word for it that I didn't mention, you might also find more literature on it under this name, is pseudo-Dirac. So pseudo, quasi, same thing. But now we're going to work on the opposite regime where he had a very large Majorana mass. And you probably derived in the problem that in that regime, the light neutrino masses basically go like this. And then there's what I'm going to call a heavy neutrino mass that is basically the scale of mu. So this is great because it means if this new scale is larger and larger, neutrino masses get smaller and smaller, hence this kind of cartoon picture. So hence seesaw. I really dislike this drawing because like that's not quite how seesaws work, and also the light neutrino getting taller and taller in this picture makes it confused. Another kind of cartoon that might be interesting to think about is one where we were mentioning that the massless particle travels um, basically unimpeded and without ever kind of flipping its chirality, being always the same type of Weyl fermion. But a massive particle would constantly switch between left and right component. So for example, here was the electron. Now I'm going to try to do this a little bit more properly with the EC bar. And you're basically flipping left-handed electron, right-handed electron back and forth. In this picture of the seesaw, the analogy is a little different. You have this neutrino propagating through space, but when it flips into the opposite chirality, it can only do so for a very small period of time, and then that flips back into the neutrino, and so on and so forth. What this means is that this small period of time has to be small because very roughly, this is kind of a very rough picture, right? Um, Uncertainty principle tells you that if this mass associated with this right-handed neutrino here is very large, the time you have available to fluctuate into the state is very small. So the deviation from the picture where you are a massless particle propagating is basically very small. So that's one way to think about the seesaw mechanism in a pictorial way. I'm not going to say much more about that other than just kind of repeat the values that you probably calculated. So if the Dirac mass was somewhere between the electron mass and the top quark mass, then the mu parameters that you need are between 10 to the 3 GeV, which is 1 TeV just within the LHC center of mass collision energy, and 10 to the 14 GeV, which is far above anything that we can test in the laboratory. And in fact, close to things that where you expect ground unified theories to live if they are a correct thing. even though the lower end of this is kind of within reach, energetically speaking, if you estimate the mixing angle that that corresponds to in this minimal seesaw picture, you get something for mixing angle squared, which is what enters in physical observables that are relevant, 10 to the minus 14 to 10 to the minus 24. So this creates a problem for the testability of these things, because not only are the particles that are new that would prove the seesaw picture, not only are they very heavy, but the mixing that they have with the ordinary neutrinos is very, very small. So the interactions that they have are very, very small. And in fact, the way to think about the interactions here is to remember that neutrinos, the active state, interact with the W boson, or sorry, this should be an electron, for instance. And if you go to the math basis, the light neutrino also interacts with the W boson, where this factor here is basically cosine of the mixing angle. And the cosine of a very, very small mixing angle is basically 1. However, the heavy neutrino, when it interacts again through the W boson, goes like the sine of this mixing angle, which is just theta. So we say that these heavy neutral leptons, oops, we say that they have weaker than weak interactions. What this means is that if neutrinos are weakly interacting because they only talk to the weak force, then these heavy neutral leptons are even less interacting because they only interact through the weak force, suppressed by the small mixing angle theta. So it's very hard to test the normal seesaw. It's incredibly challenging. And in the exercise number 2, what you did is find a variation of the seesaw that is a little bit more testable. And the general idea of what these models are doing is essentially going to a full picture. So let me just illustrate what the full picture looks like. I think I drew this at the end of our previous lecture. So you have n new fermions. And in principle, you could be 3, in which case it makes things nice and even. We have 3 active neutrinos and 3 sterile ones. And you have some matrices. And the full neutrino mass matrix, at the end of the day, the one that you care about for the light neutrinos, you can show that it basically looks like the transpose of this Dirac matrix times the inverse of this Majorana, what I'm going to call a Majorana matrix, and then the Dirac matrix. Look, this is reminiscent of our md squared over mu, right? It's basically the same thing in matrix form. But the major difference is that this matrix on the inside is an n by n matrix. And that makes a big difference, okay? So that means that there can be structures hidden inside of this matrix here that lead to behavior that we're not expecting with the 2 neutrino simplified paradigm that we have been playing with. And that's what the exercise number 2 was. And I highly encourage you to go back to it if you didn't have a chance to complete it. Otherwise, I will post the answers on the website right after the lecture now. And you can check out how you can go from something that has a very strict relationship between mixing angles and the light neutrino masses to something that decouples those two and makes neutrino masses small, not because mu is very large, but actually because mu is also small. So that's the general behavior of exercise number 2. One of the mass entries enters into the denominator, which is actually a I should say it's a lepton number conserving parameter. And then the lepton number violating parameter was proportional here in as a proportionality to the light neutrino masses. And that means you have an additional knob, an additional handle that you can reduce the amount of lepton number violation and make neutrino masses smaller and smaller. This is a very popular class of theories. It goes by the name of low-scale seesaws. Some people love this, some people hate this, but the truth of the matter is just another possibility for what neutrino masses could look like. Okay. Any questions so far? So the last thing that I'm going to say about neutrino masses is to wrap this up, is that the Weinberg operator that we were looking at had this form. And then we said, and there was some coefficient here, let me call that C. And then there was some coefficient times the VEV of the Higgs squared over twice lambda, nu. Okay, so this my random mass for the light neutrinos was coming from the Weinberg operator in this fashion. But if you note, in the seesaw picture, the light neutrino masses also have a behavior that looks like a mass term squared over some large scale, in that case mu. And you can identify this with the Weinberg operator scales and up to factors of order 1, of which I'm going to treat C as order 1. You would have something that looks like V squared over lambda. And that means, and again, the Dirac mass here also comes from the Higgs, so it's not surprising that you also get a VEV there. Basically means that you can identify in the seesaw mechanism the scale mu with the scale lambda of the Weinberg operator. And the way to think about it is the Weinberg operator is an effective operator of which that can come from the seesaw model. And the way to think about this is that you had Higgs left on, and here you have left on Higgs. Now, each one of these vertices is something that will look like a non-effective operator, is something that has dimension 4 or smaller, so it can fit into our kind of self-consistent Lagrangian. And in the middle, you have this right-handed neutrino. And you can kind of convince yourself, if you do this diagram for long enough, that once you put the Higgses to their VEVs, what you're really getting as a result of this diagram, once I go again to low energies, I replace the left doublets by my news, you have something where here you get MD, over here you also get MMD, and over here you get a mu. But that mu, because it's very large, actually enters into the denominator. So at the end of the day, you get MD over mu. And that's the equivalence between the seesaw mechanism and the Weinberg operator. So Weinberg operator can arise from the seesaw mechanism, but it doesn't necessarily have to. So there are other ways in which you can kind of open up this effective operator, for example, through some new scalar particle. So you could imagine the Higgs left on, and some scalar particle delta, or other types of fermions, which come from higher representations of SU2. In this case, we're using like a full kind of sterile neutrino, you could imagine this being a different kind of fermion that comes together with other charged degrees of freedom, for instance. Those other variations are also seesaw models, and they all give rise to the Weinberg operator. You could also imagine models that generate the Weinberg operator at higher loop orders, for instance, things that look like that. And the advantage of these models is that they still give rise to the Weinberg operator, but they come with factors of 16 pi squared times the Weinberg operator, for instance. Because it's a higher loop order, you start paying this penalty of 16 pi squared factors, and that helps you make neutrino masses smaller with a lower scale lambda. Okay, so this number can be smaller, even though just because this prefactor here. So that's all just to say that neutrino masses can be small for a variety of things. The Weinberg operator can arise from many different things. The seesaw implies the Weinberg operator, but the Weinberg operator doesn't necessarily imply the seesaw that we saw here. There are many other variations. Okay, any questions? If not, then let me just kind of explore phenomenological consequences of these types of models. And in fact, now I'm going to be thinking about light particles. And I'm going to think in perhaps a more pragmatic approach, where all I really want to do is to be able to make statements about the existence or absence of new states. As we saw before, when we wrote down this combination, right, that the low energies just gave rise to new, this is essentially what I can call a portal, where I'm attaching a new type of particle at the end of it, in this case, the new C particle. And we got a variety of different behaviors out of that choice. But in this case, one way you could think about this type of framework is this combination LT-H tilde as somewhat of a portal that carries no standard model charge other than lepton number, where you allowed to attach new particles that are fully sterile under the standard model. So the charge under all standard model symmetries of LT-H tilde, that combination is exactly 0. And the charge of all standard model symmetries of this thing, this new C, was also 0. So I'm allowed to kind of put them together in this fashion, which makes this a portal. Okay. And we explored the neutrino mass consequences of that, but you can also just think of this as like a model building tool and a pragmatic tool to try to constrain states that are beyond the standard model and are fully neutral. So why would you want to do this? Well, there are many reasons. So we saw in the first lecture that dark matter was a very big problem that made us want to go beyond the standard model. Neutrino masses, and there are many other things we could imagine. For instance, the Higgs hierarchy problem, indicating that perhaps the scale of the Higgs mass being so different from the only other scale that we know, the Planck scale of gravity, those being so different implies that maybe our ideas behind what scales should be are not quite correct. And maybe there's something actually at the low energy scales where new physics is present that will help us understand why there is such a gap. And in that case, if you're thinking about things that exist at low scales and not necessarily ultra high energies, then you want to think about particles that exist at the light scales. But if you were to add those particles on top of the framework of the standard model, you have a problem, because if they carried standard model charge, let's say there's some new state chi, if this is not zero, then it should interact with the standard model forces. And it should interact with the standard model forces through order 1 couplings, like the electric charge, whose value is 0.3, right? So that's a large number. So we should have seen these light particles already. In fact, they would just be part of the standard model in some sense. So what you want to do instead, and this is something you saw in Nicolas and Graciella's talks, is you want to add some new sector, in this case, some dark sector. The idea being that every particle inside of this dark sector is actually has zero charge under all of the standard model forces and symmetries. There are, of course, some subtleties and exceptions to that, but that's the general idea. Whatever lives inside of this thing could be some new states for dark matter, could be even this new neutrino state that carries no standard model charge. It could be some new mediator particle like a dark photon. All of those things do not directly couple to the standard model. But you can still, through the use of portals like this one that we discussed, you can still couple these two sectors. So in particular, the use of the LH tilde with nu C gave rise to all of that phenomenology and neutrino mass story that we were discussing. But there are other options, and we're going to talk a little bit about that before the end of this talk. And I'll do it more in overview mode rather than more detailed. I think the first 2 lectures were more kind of the details of the calculations and to give an idea of how the mechanics of neutrino math actually works within the standard model. Now I'm just going to tell you a bunch of facts and give you an idea of what the phenomenological consequences of different types of dark sector particles are. So I'm going to begin still with the case of the right-handed neutrino or the stereo neutrino. And we're going to go through kind of different mass scales for what this particle can be. I'll still call this a dark sector particle. It is a new sterile and fully standard model singlet state. It does not interact with anything else that we know of, if it exists. But it does have phenomenological consequences. And let me start with an oscillation picture. And this oscillation picture for this right-handed neutrino would be interesting when that scale mu, which remember is also the mass of the heavy neutrino, which in this particular case will actually not be that heavy. This will be order 1 to at most 100 EV. When that's the case, there is a new mass splitting in nature, in addition to delta m squared 2.1 and delta m squared 3.1 that you heard about from Pedro. Now there is also a delta m squared 4.1. And this thing, given this range that I told you about, can be anywhere between 1 and 10 to the 4 EV squared. 10 to the 4 is pushing a little bit, but still kind of relevant for our discussion. In this mass splitting range, what happens is neutrinos in, for example, accelerator experiments, let's imagine a new mu. When they evolve in time, they can evolve in time as partly as a nu 4. And since this nu 4 can mix with all of the flavors in principle, it can lead to an appearance type of time evolution, where new mu's turn into new e's at some point. And that, of course, happens at the same time as the typical evolution that you get from the light neutrinos. Okay. So if you look at this picture, I only drew 2 different types of diagrams. And that's because if you are in this range, and if your L over E is such that you're looking for oscillations caused by this new mass splitting, then you essentially have an effective two-neutrino model. In fact, the right way to think about this is a model where you have 3 light neutrinos that are in the spectrum, but which propagate basically with the same phase, plus 1 neutrino, which is separate and fully is nu4, and it propagates again with some phase, but this phase evolves differently from nu1, nu2, nu3 in a way that is more different than the phases between nu1, nu2, and nu3. So essentially you have this kind of two neutrino picture. That's great. It means that you can write down very simple oscillation probabilities. And in one case, for this nu mu going to nu e, if we follow basically the same rules that Pedro taught us about neutrino oscillations, you can convince yourself that this looks like UE4 squared, U mu 4 squared, times sine squared of delta m squared 3, 4, 1, L over E. So you can understand these two factors. They basically come from this first part, U mu 4 squared. And then there's another one here, UE4 squared. So that's easy to understand. And this other sign is basically the same thing we had for the normal oscillations. So now what you get is basically a small prefactor, which is basically coming from the fact that the nu4 state is a new particle. We cannot have large mixing with the known active neutrinos, otherwise we would have known and have seen it before. So these things have to be much, much smaller than 1. And you have this oscillatory function. So while in the quasi-Dirac picture, we had that maximal oscillation, in this picture for the appearance, it's basically 0, nothing really happens, and then you get some small oscillation. And that's a small effect up there as a function of L, and this is the probability. Over there, you basically have an effect that goes like u mu 4 squared, UE4 squared times 2. After this sign goes to a half. So, and at most, this appearance effect can be 4 times that, right? So this is a very can be a very small effect. And the typical numbers that people will be sensitive to are probabilities of order 10 to the minus 3 for the best experiments in trying to look for this. So the way to think about this in the context of the other oscillations is to remember that even though we wrote this probability in this form, there are additional terms which have order delta m squared 3, 1 squared over L over E, and the same thing, delta m squared 2, 1 L over E. So provided that L is sufficiently small, or E is sufficiently large, whichever may be, L over E being the right size, these other terms are basically not important. But eventually, the phase evolution between these 3 states starts being different enough that you start being sensitive to normal standard model oscillations. So that's the general picture here. I mentioned this scenario for his right-handed neutrinos because it's actually motivated by current experimental results. Perhaps not as interesting nowadays as it was, for example, 30 years ago or 20 years ago, as I think there has been more and more confusion, but not necessarily depth certificates of these particles. But there have been indications that this might be a something real. Back in 1993, which was the year I was born, by the LSND experiment, that basically saw something that was over 3 sigma significant, that was consistent with a nu mu to nu e probability. In their case, it was actually an anti-nu mu going to an anti-nu e. That was again of this order of 10 to the minus 3. And this is kind of very surprising because, you know, if we were to find this new thing, there is a light new state, light in the sense that this is much lighter than the electron, but heavy in the sense that it's heavier than the ordinary neutrinos. If we were to entertain this possibility, you have to go back and ask yourself, is this evidence for the seesaw mechanism? And then you'll be very underwhelmed because the scale mu being, for instance, 1 electron volt means that our neutrino masses, let's say 0.1 electron volt, they have to be md squared over mu, which means md squared is now 0.1 electron volts times mu, which we take to be 1 electron volt. So this basically means that our Dirac mass term has to be like of order 0.3 electron volts. So we had this beautiful theory of the seesaw mechanism. We said mu had to be very large. The seesaws, the light neutrino masses, the Dirac mass can be large, but the physical mass turns out to be very small. But if this indication, this hint of a new neutrino state by the LSND experiment back in the day, if that was correct, then you would be very underwhelmed because the amount of seesawing that is happening is very minimal. So the Dirac mass is basically of the same order as the physical light neutrino masses. So this is not really doing you any favors. So theoretically, it's kind of puzzling, but experimentally, the problem got more and more exciting over the years. So Miniboon was another experiment that observed something that was, I will say, kind of compatible. So it's not quite 2005, but around that time. And this nowadays is well over actually 4 sigma evidence for something that is, again, mostly consistent with this appearance of 10 to the minus 3. These two experiments are actually quite different in the way that they work. I will say just a few words about LSND because I find that's kind of an interesting setup, and it enters into the third exercise that you have on the website. So LSND was a pion decay at rest source, and I think that was the only exception I think that Pedro didn't talk about in his lecture. Maybe I missed it, but if not, it's always good to hear it again. So the usual accelerator picture of neutrino experiments is you have a very high energy proton, it hits a target, and the usual way you do things with these high energies is you'd produce lots and lots of mesons, for example, pi pluses and some kaons, for instance, as well as pi minuses that you can either focus or defocus depending on the magnetic horn. And those would decay to neutrinos. But now, in the current scenario, for these LSND-like experiments, they're called spallation sources and pion decay at rest sources. And if you look at the typical proton energies that they're dealing with, it's of order GeV rather than, for example, 10 GeV or 30 GeV or 100 GeV. And what that means is that inside of the target, instead of producing mesons that fly in the forward direction, what really happens is the protons hit very heavy nuclei. So in this case, it could be, for instance, mercury or tungsten or lead. And the proton, being relatively low energy basically enters inside of the nucleus, and it kind of bounces around a little bit. So here's our proton, and it starts bouncing around and shaking up from the inside out the nucleons. And that can quite often release pions, in particular pi pluses, pi minuses. After some time, and obviously this can also knock out protons and other neutrons. And this is called the intranuclear cascade. So this is from inside out kind of picture. And then the proton eventually gets absorbed into this thing, or it leaves the nucleus. But now you have a nucleus that has been kind of granted energy, and it's now in an excited state, and it wants to relax back to the ground state. And often it will do so by releasing a bunch of nucleons. Those can be also protons. And this step is called evaporation. So the main idea here is that by shooting a relatively low energy proton inside of a heavy target, you get to shake up the nucleus and release a bunch of nucleons, which is really good for producing neutrons if you want to do neutron physics. But it's also really good for doing neutrino physics because you're also producing lots of pions. And in particular, those pions are coming from this first step, which is much quicker, while this evaporation step that is more efficient at producing neutrons, for instance, that comes later. So the pions, what happens to them? Let me start with the pi minuses. Once they're produced, they're inside of this heavy and dense target. And what happens is they get captured by other nuclei, which have a bunch of protons, so it's positively charged. So the pi minuses get very efficiently captured and essentially react with the protons inside of these nuclei to produce neutrons. So what happens are pi minuses basically disappear. But the pi pluses don't get captured because the nuclei are positive, and the electrons are too light to form atoms with the pi pluses, and those pi pluses will decay. And now they produce a muon. These pi pluses have also lost a lot of energy because they are in a dense material, so they come to rest and decay at rest. So DAR means decay at rest. Once they decay, they produce the muon, and the muon can also decay into, in this case, a positron, a nu e, and a mu bar. The muon, which was produced in the pion, also travels. It doesn't have a lot of energy because it comes from pion decay. This only has basically 30 MeV of energy, of kinetic energy. And it comes to a stop again and decays. So those neutrinos get emitted at 2 points. Right? This is our nu mu, this is our nu e, and nu mu bar. And at both points, they come from decays at rest. And this is really great because pions, when they decay at rest, give you a monochromatic source of nu mu's. And the muons, when they decay at rest, give you something that has a well-defined spectrum that is very well understood. So all you need to know is how many pions are produced and how many muons come from those. And you have everything taken care of you by just knowing that this is monochromatic and this is well known. We know how to calculate muon decays. And here comes the great thing about LSMB, which was that they searched for nu mu bar going to nu e bar. And why nu e bar? Well, Peter already answered that to us. Nu e bars like to scatter on the hydrogen and this is crucial, it has to be hydrogen, to give you a positron plus a neutron. Here I'm saying hydrogen because I want a proton that is not bound. If it was bound, this proton binding energy actually makes this process less likely and often fully forbidden. So typically you want to have hydrogen inside of your detector in order to enable this reaction, which we know is called inverse beta decay. The great thing is you get the positron annihilating with the electrons in the material, emitting 2 511 keV photons, and the neutron can get captured also after some time by either hydrogen or gadolinium or whatever other material has very large absorption cross-section with neutrons to again release more energy. So this is a very clean signature, and it means that it's very hard to fake otherwise. And that was the reason why LSND was so kind of interesting, because the signal that they were using was so kind of background free. Obviously, no measurement is background free. And it was targeting a model that I would say theoretically no one expected anything to be there, but we found kind of a surprise. Is this real? Is this evidence for this stereo neutrino real? I would say nowadays is extremely, I will put here, extremely unclear. So there is huge, there was a huge amount of effort trying to search for this particle elsewhere. And in particular, things people were looking for disappearance channels, which should be related in some way to our appearance signal at LSND and mini-bloom. But unfortunately, many of these results were no. They did not find the stereo neutrino there. The same thing with a lot of experiments, they were looking for electron neutrino disappearance. Also many no results here. There are some hints in some experiments. One has to be kind of cautious into their statistical significance. I think the most interesting one at the moment is one that comes actually from a nu E disappearance measurement from an experiment called BEST. And this is again greater than 3 sigma significance, but it's a measurement that is less striking from a stereo neutrino point of view, because this one for LSND, you see an oscillation curve, so an energy spectrum, while for BEST, if you look at the details of the experiment, you're basically in a region where, and the way the experiment works, is basically an energy independent effect. So it's much harder to link it to an oscillation feature. So this is still an open question, whether these EV stereo neutrinos actually exist. There's a lot of research about that out there. And eventually, the hope is that with the short baseline program at Fermilab and replicas or attempts to replicate LSND in Japan in an experiment called JSNS squared at JPAR, we can finally put these questions to rest, whether it will be a discovery or full exclusion of these results. SBN program at Fermilab is basically very similar to the mini-bloom setup, but with these amazing liquid argon detectors that we heard about from Pedro. And JSNS squared is a very similar setup to LSND, but in a slightly different spallation source. So something that exploits this kind of low energy proton beam. Okay, any questions about this?
There are a couple.
If not, let me take.
Yeah, there are a couple of questions, yes.
Just a minor question. When you say that you know perfectly well the spectra of the neutrinos in the case of muon decay at rest, you know it because you calculate it or because you measure the spectra of the electron?
Oh, great question. So no, the muon decay is inside of this very dense and frankly like extremely dirty target because there's a lot going on. So you don't have access to the exact positron, but you know how to calculate the spectrum. So statistically, you know the prediction for the muon decay neutrino flux extremely well.
Okay.
But theoretically, the answer is that the muon decay is very well known because the weak interaction is very well known. And it's a full kind of elementary process. There's no QCD also.
Okay, thank you.
I have a question about the internuclear cascade that you mentioned before. How can we understand this proton bouncy inside the nuclei that you mentioned before in terms of the strong forces?
Oh, yeah. By the way, this is just a cartoon, right? So like it's a lot more complicated than that from the nuclear physics point of view. But the cartoon story is that the proton is not smashing the nucleus apart. So, for example, at the LHC, when they do proton-ion collisions, right, it's very high energy process. And when the proton hits the nucleus, everything kind of breaks up and you definitely exploded. In this situation, the proton kind of sneaks in. And in a sense, being in or out is kind of a weird concept here. But you can say that the wave function of the proton starts overlapping significantly with the inside of the nucleus. And it's exchanging momentum with the constituents that is not too large, as otherwise you would break up the nucleus apart. But it's sufficient enough that you can create, for example, pions, and you can kick out individual nucleons rather than break up the entire thing. So the intranuclear cascade is just a way to say that this proton is losing energy as it's like getting accommodated inside of the nucleus, and it's not breaking up apart. And in the process of losing energy, this proton is emitting and releasing pions and potentially also taking out other nucleons. Okay. But the way the protons interact with the other nucleons is through pion exchange, right? At the low energies you can think about as that. So it's a bunch of pion exchange processes going on from the inside out.
Yeah, okay, thank you.
More questions? Okay. No more questions for now.
Okay, thank you. By the way, I should say you guys are doing your job extremely well. I don't remember if I mentioned this, but your job was to not let me finish the material with questions. So that's working very well. So let me try to speed up a little bit so we cover some more material, but please keep asking questions. It's great. So let me make mu an MeV scale number. Okay, so now my heavy neutrino is something at the MeV scale. I'm not going to talk about mu in the keV scale because I think that was briefly mentioned by Graciela, and there's a whole beautiful picture here about keV stereoneutrino dark matter that deserves more than what I can say in a few minutes. But the MEV picture, so I'm not mentioning this, but in the MEV picture, this ties more with what I'm trying to do here, which is that your new state, new age, it's kind of similar in mass to other standard model particles. And that starts getting interesting for the phenomenology. And kind of, let me take, for instance, now this right-handed neutrino, let me make the mass. I'm going to call this M4. This is going to be the heavy neutrino in the 4 neutrino picture. Let me make that mass similar to the muon mass. Okay. So nu4 also interacts through the weak force, except suppressed by those small mixing angles. So now I'm going to change the notation a little bit, where the mixing angle is mu4. And I told you that things come squared in the observables. And the main picture that you have in the scenario is that the decay width of the muon comes from purely the weak interactions. In fact, let me make that very clear. It comes purely from a weak process. So here's the W, mu, nu mu, E, and nu E. And it's 2 times 10 to the minus 19 GeV. So it's a very narrow width. In terms of the lifetime, that width corresponds to 2 microseconds, basically. Now for this heavy neutrino, I can take this graph that I just drew, and I can swap these two lines. And instead of using a nu mu, I can use the heavy neutrino, which will mix with the muon neutrino flavor, and you will have essentially the same type of interaction in here with the muon. Now, I know we set M4 to be equals mu, but let me actually make this a little bit larger so that I can actually decay mu h to the muon. This is a mu minus. And now the decay width, which you can calculate for nu h, you can basically estimate it by guessing that everything is basically the same mediator particles enter, the kind of structure of the diagram is the same. So this is roughly just u mu 4 squared, which entered here, times gamma mu, the muon width. And what that means is that the typical lifetimes for this particle, sorry, I'm swapping 4 and h, is essentially 2 seconds if u mu 4 squared is 10 to the minus 6. So that's telling you is muons are relatively long-lived as far as standard model particles go. But nu 4s, this new type of thing, depending on the mixing angle, can be extremely long-lived. 2 seconds is an eternity as far as like fundamental particle decay lifetimes goes. So these particles can travel significant distances before they decay. And that's something you're going to explore. You can explore in one of the exercises as to how this thing can be observed. And if I go to the picture of accelerator experiments, where you had lots of pions and kaons, these pions and kaons can also produce, not only do they produce neutrinos, for instance, mu plus, nu mu, but I can, again, remember, replace this by a heavy neutrino if kinematically allowed. Let me make this a little bit more exciting, because now it's kinematically allowed. I can replace that, in this case, by UE4 squared, for instance. So pions and kaons, another possibility is a kaon can decay to an electron or a muon in U4, again, by paying the price of these mixing angles. So a neutrino experiment can be a source of these Nu4 states. And then at your detector far away, that Nu4 can come in, being basically invisible, and decay into, for instance, a mu plus and an E minus, like we have here, or a mu minus and an E plus. And what that gives you is something that basically comes in as invisible and then suddenly produces a visible final state. There's also an invisible neutrino that comes out, but that you cannot observe. So that's one way in which you can look for these particles, is an anomalous appearance of these exotic final states. In this case, you look for mu-E final states in your detector. One last thing that I will say is I used mu plus E minus as one of the decay rates, but you can also do mu minus E plus. And if your heavy neutrino is of a Majorana type particle, both of these processes are available to you, because the lepton number of this of this particle is not really well defined because the lepton number is violated. So I can either remember that there's another neutrino involved, right? So in this case, it's a nu E, and in this case, it's a nu E bar. And the lepton number of these two final states is actually 1 and -1, but you can actually decay to both of them. And that's kind of a smoking gun that the particle that you produced in this beam through this exotic way, if it decays the same way to both final states, that you have a Majorana particle there that you can look for. This also brings me to the general point that in general, in this beam, pi plus, k plus, pi zeros, etas, and a bunch of other things, they can all produce dark sector states. And those dark sector states can then scatter or decay inside of those neutrino detectors, which makes neutrino experiments extremely useful for looking for these dark sectors. And the basic reason is that the number of these things that you produce in a neutrino experiment can be well over 10 to the 21. So even if 10 to the minus 20% of the time of a pi zero decays into a new state, if that one new state actually does survive to your detector, you have 1 particle or 10 particles in that case to look for. So you can probe extremely small branching ratios if you have a very good way of catching the produced particles. In the case of decay, the larger the fiducial volume of your detector, the better. In the case of scatterings, the higher density your fiducial volume, the better, because your new dark states can scatter more often. And that's basically what we're doing with neutrino experiments, is having large volume and high density materials. So obviously I had a lot more to say about different types of new physics, but I think my time is running out. If I may, I just want to end with one kind of concluding type of remark, and that's neutrinos are very useful tools for BSM. This we didn't talk as much, only in today's lecture, for what I would say 3 reasons. I think in Pedro's colloquium, there was one main reason, which I'll definitely agree with, which was that neutrinos interact only through the weak force. So any kind of new physics, whether it be in the type of interaction or a new particle produced, any type of very rare and weakly interacting new physics, it can only be as weak as the weak interaction, and we would already be sensitive to it. So neutrinos are good because of that. They don't interact very strongly, which means that rare interactions in the dark sector would be more prominent on top of what they are already doing. The second reason I would say is that neutrinos actually propagate macroscopical distances and reveal quantum mechanical effects at macroscopical distances. So the phase evolution of the state happens in macroscopical distances given by very small mass splittings. And that makes them what I like to call Earth-sized quantum devices, which is basically a way to say you're exploring quantum mechanics and potentially very, very small effects on the phase evolution of particles over extremely large distances. When you take this to IceCube and astrophysical neutrinos, that becomes even more relevant because you're propagating such long distances. And finally, I would say the other reason why neutrinos are very good tools is that they're essentially a very bizarre component of both the universe, is basically 40% of what's considered radiation in the early universe, but also in astrophysical settings. They reveal things about the inner side of astrophysical bodies and supernovae, for instance. So they have a very interesting kind of collective phenomena, both in early universe and astrophysical scenarios, which is unique. And all of these options are basically very good for exploring ultra rare, kind of difficult to observe effects. So I'll stop here with this kind of general conclusion. I hope I convinced you that this is an interesting topic, not just from the foundational issue of neutrinos as BSM because of neutrino masses, but also from neutrinos as a tool. I'll be happy to talk more and answer any of your questions now. So thank you.
Good. So now we go to the question session. So we take questions for Matheus, but also we can take questions for Pedro. And if you have questions about cosmology and dark matter, I maybe try to answer them since Graciela is not here. So yes, open microphone. Yes?
Yeah, I have a question about cosmology precisely. And I just was asking about what is the significance of chemical potential in the in cosmology. I don't get it at all.
So good question. I don't think I can answer, but chemical potential is usually associated with chemical reactions. And usually we have equilibrium, so chemical potential is zero. So in some phases where you are producing a lot of particles, that changes. But I don't know which specific question you have. So usually when you have transitions,
Maybe some more specific will be for particles in cosmology, just like neutrinos or dark matter. So what's about the chemical, what is the role of the chemical potential in those particles? Yeah, I think that's more clear.
okay. So yeah, so normally we think we have either Fermi, Dirac, or Bose-Einstein distributions, and we have this chemical potential there. But normally, in like most part of a universe life, let's say, the particles evolve independently from each